Alright, so in this video we're looking at the Poisson probability distribution. So the little blurb here, another probability distribution for discrete random variables is known as the Poisson distribution. It's used to determine the probability of a number of events occurring over a specified time or space, named for Simeon D. Poisson. Alright, so some examples of events that occur over time or space: number of cells in a specified volume of fluid, number of calls per hour to a helpline, number of emergency room beds filled per 24 hours. It could also be a number of emergency room visits over a 24-hour period, right? But the key is that it's over a length of time, right? So, like the binomial distribution, normal distribution, there are many Poisson distributions depending on key parameters. Right, so that the average rate at which the event occurs is what we're talking about there. All right, the capital X represents the number of occurrences in a continuous interval. Mu is the expected value of occurrences in this interval. All right, so how many emergency room visits did you expect to have over a 24-hour period versus how many actually occurred? All right, conditions: the probability of an occurrence is the same for any two intervals of equal length. The expected value of occurrences in an interval is proportional to the length of this interval. All right, one is a consequence of the other. The occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. All right, so the 24-hour period for emergency room visits selected would be independent from any other 24-hour period that would be selected. And the probability of two or more occurrences is very small, or I'm sorry, in a very small interval is very small, so close to zero. All right, so this is the Poisson distribution. We have exponential e raised to negative mu times mu to the I power over I factorial. Depending on what I is, this would take a variety of different forms. All right, so alternate notations: e of x, also known as mu, and you have the variance of x is actually going to be equal to the value of mu, which is kind of nice, but that's also, or can also be written as sigma squared is equal to mu, or we could write it as sigma is equal to the square root of mu. All right. So the Poisson distribution actually has that aspect to it where the variance and the expected value are the same. All right, so here's an example, a guided example. Suppose the average number of car accidents on the highway in one day is 4. What's the probability of no car accident in one day? What is the probability of one car, that's a heck of a typo, accident in 2 days? All right, so you look at the setup here. We have e to the negative 4. That's because the expected value, mu, is equal to 4. All right. The I we leave variable so that we can evaluate it depending on what the question's asking us. When it says no car accident in one day, that would be the case where x is equal to 0. When it says one car accident in 2 days, now that's a little bit of a kind of a different situation here because it's in 2 days. So that's going to change the expected value. We would expect there to be 4 car accidents in one day. So if we're going 2 days now, we would expect there to be 8. All right. So the first part of the problem here, we're taking our function model and replacing the I with the 0. If I can make this fit. And in the second part, we're replacing not only the I gets replaced with a 1 because it's probability of one car accident, so that'd be the x value. but the mu value is also changing. The mu value becomes an 8. Now, we can run all these numbers in Desmos, and I'll show you how to do that in a sec. Right, so there's a couple ways of handling that. One way, let me just open a fresh new Desmos here. One way would just be to type it in straight away. So we would have a fraction, type in e, exponential e, raise that to the -4, multiply that by 4 to the 0th. Well, anything to the 0th is going to be equal to 1, but I'll type it in as 4 to the 0th anyway. And then put it over 0 factorial. And so we would get about 0.0183. All right. For the second part, all we're doing is replacing the 4, or any 4, with an 8, and any 0 with a 1. And so that's where we get our 0.00, which is really 00268. If we want to be correct with our rounding procedures. All right. So, looking at the example that follows, I get this thing here, I don't even know why it's there. Suppose the average number of calls to 911 in 1 minute is 2. So that's an expected value. What is the probability of 10 calls in 5 minutes? All right. So this is the mu for 1 minute. If I'm talking about 5 minutes, well, I wouldn't expect there to be only 2 calls in 5 minutes if there's 2 calls in 1 minute. So mu is now 10. All right, that's 5 times 2. All right. So we want to know the probability of getting 10 calls in 10 minutes. All right, so that's the same as saying find the probability that x is equal to 10, and that's going to be e to the negative expected value times the expected value raised to the I power. I is going to be dependent on the discrete value that we're choosing, in this case 10, so 10 to the 10th, it's going to be huge, over 10 factorial. So huge numbers divided by other huge numbers. All right, so I'm going to pop this into Desmos. So e raised to the -10th multiplied by 10 raised to the 10th over 10 factorial, so about 0.125. Now if you go into Blackboard in Unit 2 under the calculators, under Calculators Unit 2, you'll see one that says Poisson Distribution. So it's all set up and ready to rock and roll. All right, so the I values, I put them in as a series of, or a sequence of values going from 1 to n. All right, so the I, in this case, we want it to be 10, so I've dialed that up to 10. The mu is also 10. All right, so this gives you a look at what the Poisson distribution would be like. Now it's really compressed. So instead of going on the y-axis from -8-ish, I'll make it go from 0. And instead of going up to 5, I'll have it go to like 1. You get a better look at the Poisson distribution, which is very normal. A very normal distribution looking graph for these particular values. All right, so as a discrete random variable, you can see the function's already popped in there. For I equal to 10, we get the 0.125. All right, now if we needed the mean and the standard deviation, we could pull that out from this Desmos.